900 million miles from the sun, a camera built to look at the birth of galaxies turned around and pointed at a moon instead. What it found didn't match the forecast. Saturn's largest moon, Titan, was supposed to be quiet that season. Its northern summer was just beginning, and the old models said the skies over its lakes should be calm. Instead, the James Webb Space Telescope caught something moving. Bright spots, flaring and shifting, climbing higher in the atmosphere over the course of a single day. Clouds, behaving in a place where clouds weren't supposed to be building yet. Then came a second signal, buried in the infrared light, that no one had ever separated out of Titan's atmosphere before, a molecule so short-lived it should have been chemically invisible from 900 million miles away. Two mysteries, one moon, one telescope, not designed for this job at all. This is the story of what Webb saw when it looked at Titan for the first time, and why some of it still doesn't add up the way scientists expected. Titan is not just another gray rock orbiting a gas giant. It is the only moon in the solar system with a real atmosphere, thick enough that sunlight struggles to punch through the haze. It is the only place beyond Earth with rivers, lakes, and seas sitting on its surface right now, and it runs on a weather cycle that looks almost like ours, except every part of it has been swapped for something colder and stranger. On Earth, water evaporates, rises, cools into clouds, and falls back as rain. On Titan, the working fluid is methane. At minus 179 degrees Celsius, methane behaves the way water does here. It pools into lakes, evaporates into the sky, and occasionally comes back down as an oily, freezing rain. Scientists call this Titan's methane cycle, and for 2 decades, it was mostly studied from a distance by a spacecraft that no longer exists. That spacecraft was Cassini. Between 2004 and 2017, it orbited Saturn and repeatedly swept past Titan, mapping its northern lakes, its dune fields, its seasons, and even dropping a small probe called Huygens onto its surface in 2005, the first landing anyone has ever made on a world in the outer solar system. But Cassini's mission ended before Titan's northern summer really got going. When Cassini burned up in Saturn's atmosphere in 2017, Titan's north was still just waking up from its long winter. Nobody had a spacecraft in position to watch what came next. That's the gap James Webb was never meant to fill. Webb was built to study the first galaxies and the atmospheres of planets circling other stars, tens or hundreds of light years away. Pointing it at a moon inside our own solar system, a target that's comparatively close and comparatively bright, is almost an act of borrowing, using a deep space instrument for a near space question. But a team led by planetary scientist Connor Nixon at NASA's Goddard Space Flight Center did exactly that, in November 2022 and again in July 2023, and paired Webb's data with observations from the Keck 2 telescope in Hawaii. The goal was simple to describe and hard to pull off. Catch Titan's northern hemisphere in the act of building weather, and figure out what its atmosphere was actually made of at different altitudes, not just averaged across the whole disk. What came back did not look like a quiet moon settling into summer. Here's where the science gets specific, and it's worth slowing down for because the mechanism is the whole story. Webb doesn't take a normal photograph. It captures light at very precise infrared wavelengths, and different wavelengths on Titan correspond to different depths in its atmosphere. Light at one wavelength comes mostly from high in the stratosphere. Light at another wavelength comes from lower down, in the troposphere, where actual weather happens. By comparing images taken in different filters, and comparing images taken days apart, the team could do something close to X-ray vision on Titan's sky, watching where bright cloud features sat in altitude and whether that altitude was changing. And it was changing. Across the observation windows, clouds that had been sitting low in the troposphere on one day appeared higher up just days later. That upward drift is the signature of convection, warm gas rising, carrying material with it, the same basic physics that builds thunderheads on Earth, just with methane standing in for water vapor. This wasn't the first time convection had ever been spotted on Titan. Cassini had caught hints of it in the south years earlier, during Titan's southern summer, but this was the first time it had been documented in the north. And the north is where it actually matters most, because that's where the majority of Titan's lakes and seas sit. Kraken Mare, Titan's largest sea, is up there, and its combined northern seas cover roughly the same surface area as North America's Great Lakes. So is most of the standing liquid on the entire moon. There's another wrinkle that makes Titan's weather harder to picture using Earth intuition. On Earth, the troposphere, the churning, weather-making layer closest to the ground, only reaches up to about 12 kilometers before you hit the stratosphere. On Titan, because gravity is so much weaker, that same weather layer stretches nearly 4 times as high, up to roughly 45 kilometers. Titan doesn't just have a different fluid running its weather, it has a taller, slower sky for that fluid to move through, which is part of why a cloud rising in altitude over a few days, rather than a few hours, still counts as fast by Titan's standards. If methane clouds are actively forming and raining over that hemisphere, It helps answer a question that had been nagging at planetary scientists for years. What keeps those lakes full? Titan's methane doesn't just sit there. Sunlight and radiation in the upper atmosphere are constantly breaking it apart, a process that, left unchecked, should slowly drain the moon's methane supply over geological time. Rain replenishing the lakes from clouds like the ones Webb caught in the act is part of the answer. Not the whole answer, part of it. Because here's where the second signal comes in, and it's the one that made this genuinely unexpected. Buried in Webb's mid-infrared spectrum was the fingerprint of a molecule called the methyl radical, CH3. Not methane itself, CH4, which is stable and common and had been mapped many times before. The methyl radical is what's left over in the instant, after sunlight or charged. Particles rip a hydrogen atom off a methane molecule. It is chemically aggressive, and it does not last. Within Titan's atmosphere, it either reacts further within moments or gets swept up into longer, heavier molecules almost as soon as it forms. That's exactly why nobody had ever spectroscopically detected it before. Catching CH3 is like trying to photograph a spark instead of the fire it's about to start. You have to be looking at the right altitude, at the right time, with an instrument sensitive enough to isolate a signal that exists for a heartbeat, chemically speaking, before it's gone. Webb caught it anyway. One researcher on the team described the discovery this way. Earlier observations of Titan's atmosphere had only ever captured two ends of a process: the methane going in and the heavier organic molecules like ethane coming out, years or eons later. What Webb caught was the middle step, the actual moment of transformation. Not the flour and sugar and not the finished cake, but the batter, rising in the oven, mid-reaction. That distinction matters more than it might sound like it does. Titan's hazy orange atmosphere is loaded with complex organic chemistry, the kind of carbon-based molecule building that, on early Earth, is thought to have been a step on the road toward the chemistry of life. Nobody is claiming Titan has biology. Its surface is 180 degrees below zero, and its water is liquid methane. But the same fundamental chemical machinery, breaking simple molecules apart and rebuilding them into more complex ones, is running there right now in a natural laboratory scientists had never been able to catch mid-process before. So put the two findings side by side. Convective clouds, building and rising in a hemisphere that was supposed to still be quiet, and a fleeting chemical intermediate, direct evidence of active organic chemistry, detected for the first time in Titan's atmosphere. Neither discovery on its own would have been shocking. Cloud convection had precedent in the south. Organic chemistry on Titan had been theorized for decades. What's harder to explain away is the pairing, an atmosphere caught doing more, chemically and meteorologically, earlier in its seasonal cycle than the standing models expected. Titan's year lasts nearly 30 Earth years, and its seasons crawl by slowly enough that a research team can spend an entire career watching only a fraction of one full cycle. The Cassini-era models were built on partial data, mostly from Titan's winter and spring. Northern summer had barely been observed by anything at all before Webb and Keck turned their instruments toward it in 2022 and 2023. What counted as on schedule was, in a real sense, still a guess. There's a second oddity worth putting on the table, one that isn't from these particular observations, but sits right alongside them in the broader puzzle of Titan's surface. Where Titan has rivers flowing into its seas, scientists have long expected to find deltas. The fan-shaped deposits of sediment that rivers build up where they slow down and empty into standing liquid, exactly the way they do on Earth and even on Mars. Researchers studying Titan's coastlines have instead found the deltas are largely missing, and the rivers are there, the seas are there, the expected sediment fans mostly aren't. It's the kind of gap that suggests either Titan's sediment behaves in ways nobody has modeled correctly yet, or something about how quickly liquid levels rise and fall on Titan prevents deltas from ever building up the way they do here. None of this is being framed as a single grand anomaly. It's smaller cracks, showing up in different corners of the same investigation, all pointing at the same conclusion. Models of Titan, built mostly from Cassini's winter and spring data, don't fully predict what a Goddard-led team is now watching happen in its summer. Each individual gap is explainable on its own. Stacked together across cloud behavior, atmospheric chemistry, and surface geology, they start to look less like noise and more like a pattern nobody has fully mapped yet. At this point, it's worth being precise about what is actually established here, because a story like this can drift into overclaiming if you let it. What's established? Webb and Keck observed real, moving cloud features in Titan's northern hemisphere in 2022 and 2023, and the altitude changes in those features are consistent with convection. Webb's mid-infrared spectrum shows a genuine detection of the methyl radical, published in Peer, reviewed in the journal Nature Astronomy in 2025, led by Connor Nixon's team at NASA Goddard. These are measured signals, not inferences from a single ambiguous data point. What's interpreted, and reasonably so, that this convection is part of what replenishes Titan's northern lakes, and that catching CH3 directly is a rare window into organic chemistry happening in real time in the atmosphere. What's still open, exactly how typical or atypical this timing is within Titan's 30-year seasonal cycle, since there simply isn't a complete data set spanning a full year to compare it against. The team was not able to directly observe precipitation falling. They saw the clouds rise, which strongly implies rain is following, somewhere behind them. But the actual raindrops reaching Titan's lakes were not caught on camera. And the missing river deltas remain, for now, an open question about Titan's surface geology rather than a mystery Webb itself was built to solve. That gap between here's what happened and here's why it's happening on this particular schedule is exactly the gap that made a moon nobody expected surprises from. Into a moon that just handed scientists two of them in the same set of images, it also raises the stakes for what comes next. NASA already has a spacecraft built to go there. Dragonfly, a nuclear-powered multi-rotor lander about the size of a car, is scheduled to launch toward Titan later this decade, with plans to fly from site to site across the moon's dune fields and hydrocarbon lakes, sampling its chemistry directly instead of watching it from 900 million miles away. Everything Webb and Keck learned about where the clouds sit, how fast the seasons are actually shifting, and what the atmosphere is doing chemically in real time will shape exactly where Dragonfly is sent first and what its instruments are tuned to look for the moment it touches down. Which means the story doesn't end with a strange spectral line buried in a 2023 dataset. It ends with a machine already built, on its way to go stand in Titan's oily rain and find out, on the ground, whether the sky really is doing what a borrowed space telescope caught it doing from very, very far away. Dragonfly won't just watch the clouds from orbit the way Webb had to. It will land in them, sample the surface chemistry directly beneath wherever those methane rains actually fall, and send back the first ground level answer to a question that, right now, still depends on inference from 900 million miles out. For now, the picture is this: a moon with rivers, lakes, and seas of liquid hydrocarbons, an atmosphere quietly manufacturing the organic building blocks of complex chemistry, and whether that showed up earlier and moved differently than 3 decades of Cassini-based models predicted it would. Something in Titan's sky moved off script. Webb just happened to be the first instrument sensitive enough, in the right place at the right moment, to catch it doing it. So here's the question worth sitting with. If a telescope never built for this job can catch a hidden atmosphere shifting its own chemistry mid-reaction, what else out there has already changed, quietly, before anyone was watching closely enough to notice?